Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. This time we're going to talk about the appearance and structure of other galaxies. We went through an extended dance remix of exactly what the Milky Way looks like as a galaxy, and we discovered that it is the galaxy, meaning our home galaxy, and we learned from Edwin Hubble that all the other spiral nebulae are extraordinarily distant objects extremely far away, and that our Milky Way is one of many, quote, island universes. But what we really learned is that there's lots of different types. And so once Edwin Hubble started doing a major photographic survey, he showed us that the cosmos is filled with these extraordinarily large distant objects. So let's go see what they are. Hubble, during his work in 1926 to 36, once he started really going to town with that 100-inch telescope at Mount Palomar, he took numerous photographs of the night sky, made amazing discoveries, and found that the bright galaxies in the sky, we're talking the bright galaxies now, fall into three broad classes according to shape. So he simply took photographic visual surveys of them and determined their classes according to shape. So we're going to follow in Hubble's footsteps in terms of looking at visual representation or optical light representations of the various galaxies. And so Hubble's tuning fork is how he thought they would, thought that they had some kind of significance. And he thought that they naturally progressed from one to the other. And so he had that 75% of all the bright galaxies were spirals, about 20% seem to be ellipticals, and about 5% are some sort of irregular, which don't fit any pattern. And this is his tuning fork diagram. And he thought that actually progressed from left to right, from elliptical to spiral, thinking that go from a simple looking thing to a more complex looking thing. But we now know that the Hubble tuning fork diagram has no intrinsic meaning. It just looks nice and is very helpful to help you remember the different types. So you can see we have different things, beginning with E's, those are the ellipticals, and we have the S's, those are spirals, and then there's the upper tree of spirals, and the lower tree, which are the barred spirals, or the SBs. And the bars have a bar across, and the irregulars, well, they're kind of like train wrecks. So let's go take a look at all of them. From this point on, we're going to do an incredible visual survey, because you've probably not seen a lot of different kind of galaxies. So it's my job in this particular lecture to give you a whole bunch of images and show you what the galaxies themselves look like. So here we go. Hubble's classification scheme looks a lot like this with ellipticals and spirals, so let's go take a look. I derived all of the images that you'll see in this particular thing from lots of different sources, from the National Optical Astronomical Observatory, from AAO, the Australian Astronomical Observatory, the Gemini Observatory, European Southern Observatory, the Keck on Mount Mauna Kea, lots of things from Hubble Space Telescope. In fact, I even went to the SEDS group, and then there's a guy that does the NGC project trying to take pictures of all the NGC objects, and then looking at the NED database, which is the NASA Extragalactic Database of Galaxies. So you can look at all of these things to find all these images, and everything I've done here comes from these places. And a lot of these then also appeared in Astronomy Picture of the Day. So if you Google APOD, you'll also see many of these. All right. Elliptical galaxies are elliptical in shape. They don't have any internal structure. They don't have disks. They don't have spiral arms. They don't have dust lanes. The brightest stars are big red supergiants, and they're classified only by their appearance and their apparent flatness. So if you see a circular looking one, that's an E0. And if you see one that's really wide compared to its height and it's really flat or smushed or cigar shaped, then that is an E7, where it's up to about 3 times as wide as it is high. Ellipticals come in huge size differences, from some that come from trillions of stars down to tiny little dwarf with only a few million stars, which is smaller than some globular clusters. They also contain no gas or dust and show no evidence of star formation. So they do have lots of hot, but ellipticals do, however, tend to have really large hot clouds of extraordinarily hot gas emitting in X-rays that extend far beyond where you can see. So they may be very well embedded in very, very, very large X-ray cloud emitting gas. So that's interesting. All right, so this is a classic elliptical galaxy. It's a giant elliptical, and it's M87, and it's part of the Virgo cluster of galaxies. And this was taken by the CFH telescope at Mauna Kea. It was an enormously fun look to see, and so when you look out, you see it's got an elliptical shape. It's pretty yellow, and there's a lot of stars, and it's a kind of a glowing cloud. And let's go see more ellipticals. This is the Elliptical Galaxy 1132. It seems to be in the middle of a whole number of tiny little galaxies. It's a giant elliptical, and you can see a number of little galaxies all around it. Here's another giant elliptical galaxy. All right, we keep going through it, and another elliptical with some spirals that are much more distant in the background. And again, I believe this is M87 that we saw before in Virgo. And you can see a number of other ellipticals, at least 4 others that are there, maybe 5 or 6. Actually, Google, if your eye wanders around, you see a lot of them, plus a lot of other fuzzy objects in the background too. If it's got basically spikes, like those starry spikes, that's a Milky Way star. That's a star in our Milky Way. We're mostly and completely concerned with all the fuzzy objects that are in our field of view. Those things are much more distant. M87 in the Virgo cluster of galaxies is over 65 million light years away, and so it's truly distant compared to the stars in the field, which are only tens of light years to thousands of light years away, and maybe up to 10,000 light years away. But stars are on the order of hundreds to thousands of light years away in pictures like these, but galaxies are on the order of millions or tens of millions, if not hundreds of millions of light years away. And this particular one in the center, that is in the Virgo cluster, which is about 65 million light years away. Incidentally, the light from this galaxy started traveling to us at about the same time that the dinosaurs were wiped out on Earth. So that's what it looked like back then. We see it now. Here's another image of an elliptical galaxy, and another one is a very, very elongated elliptical, and now a more centrally looking elliptical. Lots of ellipticals. Oh my goodness, ellipticals. There's an E0 type, definitively, and other ellipticals, and so on, and so on. The Virgo cluster has a lot of elliptical galaxies in it. We see 4 examples here, ranging from E0 and ranging from a dwarf in the lower left to a very large E7 type elliptical in the upper left. All right, so ellipticals, can be looked at as kind of boring to put up, and you're not going to make a really big poster of an elliptical galaxy and put up on your wall, because people go, why you got that big white dot on your wall? But we're going to get to the more pretty looking galaxies very soon. The next intermediate type in the Hubble scheme is the S0 types, and they are the lenticular galaxy. And lenticular means lens-shaped. And there's also barred lenticular, SB0. They do exist. So they're distinguished by having a bar type of shape in them, but they're rarer. So now a lenticular does have a disc-like structure. It does have a central bulge, but there aren't any spiral arms, and there's no interstellar gas. So you don't see any hydrogen gas clouds or anything like that. A lenticular galaxy is seemingly intermediate between ellipticals and spirals just because of the appearance. And they do have dust in their disk. So an elliptical can have dust lanes, even though there's almost no star formation going on. So that means the hydrogen gas is gone, but there's still dust left over, which is interesting. But because if they have very ill-defined arms, and if they're face on, meaning you see most of them from the side, you won't necessarily see that dust, and a lenticular can easily be mistaken for an elliptical if they're not seen edge on. All right, so here's a classic lenticular, meaning that you see just a fuzzy cloud, and that fuzzy cloud is very much like an elliptical galaxy, but yet it has a dusty lane going through it. But there's no pink clouds in that indicate star formation. So this is a standard sort of typical lenticular. Here's another lenticular. I believe it's actually the same one. No, it's a different one, but they look very similar, don't they? Here's another lenticular with a seen edge on, and you can see there's dusty lanes in them, but there's no pink star formation, so it's all older stars. Here's another lenticular, and you can see that they can have spiral arms to them, but the spiral arms there's no star formation. There's no pretty little Orion nebulas or Trifid nebulas or anything, or Tarantula nebulas or anything like that. There's nothing like that, but there are dusty lanes inside of them. So these are kind of reddish sorts of galaxies. Here's another lenticular. We see it's kind of wispy, and there's some dusty lanes in the middle, but it mostly looks like a lot of older stars. Another lenticular, dust lane again. There's a standard appearance, and they tend to be kind of small. This is about only on the order of a few thousand light years across, and it's about 25 million light years away. So it's closer than the Virgo cluster of galaxies. But yet, what we see is there's a dusty lane, and then some appearance by some of the cloudiness for it. But that cloudiness is obscuring some of the dust lanes. So it's kind of in between an elliptical and a lenticular. All right, let's get to the really pretty stuff. The ordinary spiral galaxies. So spiral galaxies come in a few flavors, and we will call them S, A, B, C, and D. Now, Hubble did basically S, A, B, and C, and there's been some extensions and slightly different things, but let's add the SDs because they do exist. So an SA will have an enormously large bulge and very, very, very tight, indistinct arms. So they look a little like a lenticular, except there's star forming going on. An SB are an intermediate type. They don't have as large a bulge, but the arms are much more distinct. And SC are of a tiny bulge and loose, very well-defined arms. And SD has absolutely no bulge, but lots of big spiral arms. So these tend to be really pretty, so here we go. This is the classic SA type galaxy, the Sombrero. It's about just under 30 million light years from Earth. It's about half the size of the Milky Way at 50,000 light years across. And inside of here, there is some star forming going on. Not a lot, but you can see that if you squint and look carefully, you can see there's some pink clouds in there. So this seems to be like a extremely dusty lenticular type galaxy. But that's where we think of that's why Hubble merged into this tuning fork diagram, because they seem to, by appearance, merge smoothly one to the other. But that doesn't mean they evolve this way. They just have this certain appearance. And so there's only certain ways that a galaxies certainly appear. Well, inside of those dusty bands, there's some pink glows, and those pink glows show star formation. All right, another one is the classic spiral called M81, and M81 lies about 12 or so million light years away, and it's an incredibly beautiful spiral galaxy, and it's one of those intermediate SB types. We can see definitive spiral arms. There's bright pockets of star formation indicated by the blue glows, and there's some pink glows as well, indicating ongoing star formation. And this is another view of it. And then we see with the Whirlpool Galaxy, extraordinarily vigorous star formation happening. That's what all the pink glows are. Those pink glows indicate Orion nebulas and hot H2 regions, meaning ionized hydrogen. That's where the pink glow comes from. And inside of the pink glow, we see are that's where bright stars form in clusters and groups. And as the galaxy itself rotates, or more specifically, everything rotates through it, gas passes into these spiral arms, these overdense regions, gets compressed, as we saw with the formation of the Milky Way spiral arms, and then stars are formed and keep traveling on and then explode as supernovae. So basically, you see dust on one side of the spiral arm, and inside of the spiral arm, vigorous star formation and pink clouds, and on the other side of the spiral arm, as they travel through the density wave, are the bright stars that were formed by the gas only a few million years before. So you can think of it as that. Look at it from one side of the arm to the other, and the extent of the blue stars doesn't get very far from the spiral arm. So they'll only go about 10 or so million years. So that span is just how far they go in 10 million years. All right, so let's get deeper in close to the center of the Whirlpool Galaxy, M51. You can see more of what I was talking about, meaning the spiral arms are places where star formation is vigorously occurring. And this is the Pinwheel Galaxy, M101, which is also an SC type galaxy, a very small bulge but large and loose spiral arms. And if you look really closely, there's a wonderful detail of it. You can see the flow of the gas. You also see how the stars themselves are grouped in large groups. There's not as much pink star formation going on. And what's neat is about this particular image is way off to the right, we see another galaxy. And that galaxy is extraordinarily distant compared to M101. So we're looking through the galaxy to an extremely distant galaxy, maybe 100 times further away. That's an amazing image right there. But what we can see, remember we talked about the nature of how spiral arms are basically the gas and dust is on these streams of elliptical orbits. So look at the shape of the gas. It looks like it's in waves. But now think instead of them being in waves, think of them as lines. And so the lines are orbiting the center. And so you have like this nested set of ellipses, and when they run into each other, they get denser and darker. All right, here's the Triangulum Galaxy. This is a local little neighbor within a couple million light years, and it's a favorite target for amateur astronomers and for amateur photographers because lots of really great star formations going on. See, that's that pink glow. It's also an SC-type galaxy with a very tiny core, bulge, galactic bulge, and very well-defined arms. And another one is a starburst galaxy called NGC 3310, where there's huge amounts of star formation going on. That's why it's got really bright all over the place. It's about half the size of the Milky Way, and it's about 50 million light years away. And to cause that, it probably was a collision with another galaxy, maybe 100 million years ago, and these stars are now the brightest of stars. And we can estimate that they would be 100 million years ago, because the types of stars are roughly A-type stars. O-type stars live a few million years, B-type stars live tens of millions of years, but if the spectra of the stars is roughly A-type, then they'll live about 100 million years before dying. And that is the kind of stellar spectra that we would see inside of this galaxy. All right, here's another great spiral, Messier object number 74, with numerous star formation regions and quite distinct things, distinct images. And these Hubble heritage images are fantastic, so go definitely Google these around. And if we look closely, we have M81 and M82 close together in the sky. These are an interacting pair at about 12 million light years away. And this is the Leo triplet, a triple of spiral galaxies in the constellation Leo. And you can this image is about 1 degree across. So if you have a large enough telescope and the eyepiece lets you see about 1 degree across, for a standard, for something that's an f2, f4 type telescope, if you have a 17 millimeter eyepiece, this would all fit inside the same eyepiece, which is I've done. So it's kind of pretty. So we see three different spiral galaxies, and yes, they're an interacting group. The spiral galaxy NGC 1309 has another little distant spiral up and to the left, and a much more distant spiral off to the right at 3 o'clock. And then you can see huge numbers of spiral galaxies way off in the distance. And so clearly we were looking not along the plane of our Milky Way, which blocks the light of these stars, but above or below the Milky Way in order to see this object. So look at all the little tiny smudges in the background. Those are even more distant galaxies, far in the distance. And there's another one, another beautiful grand spiral. We can see little tiny smudges. Each of those are much more distant galaxies. Here it is again, and the spiral galaxy NGC 3370 is chosen because it has some beautiful galaxies in the same field of view. An edge-on lenticular on the lower right, lower center, and it looked in a tiny barred spiral in the upper right, as well as numerous little galaxies. Those aren't little because they're little compared to NGC 3370. They're little because they're really far away. So the universe is filled with these things. So here's another one, NGC 3949. I love showing these off because they're really pretty. And there's another one, and you can see the spiral arm structure, and there's another beautiful one. And you can see that now the two elliptical, there's actually a number of elliptical galaxies that kind of surround the spiral. And yeah, they seem to come in groups like this. And here's another classic spiral, which has huge amounts of dust. And there's the Starburst galaxy again, just because. And now we can see what a spiral galaxy looks like edge-on. I believe this is NGC 891, and it's a classic edge-on spiral galaxy. How do we know it's a spiral galaxy? because of the huge amounts of dust and gas, and the spectrum shows star formation and hydrogen gas cloud emissions. And there's another edge on spiral galaxy, and we know it's a spiral because of the star formation that's happening in it. And that star formation can be seen by the glow of hydrogen and the prevalent blue glow of stars in the disk. Remember again that the dots that we see in front of the spiral galaxy are part of our Milky Way, and so therefore very close. And there are little tiny smudgy galaxy-like objects in the very far background which are much more distant than the foreground galaxy. And this galaxy is on the order of tens of millions of light years away anyway, so that's pretty far. The stars are near at tens to hundreds of light years. Then the galaxy is millions of light years, and the much more distant little background galaxies are probably 100 million light years or more. There's a lenticular and a distorted spiral galaxy, and another. Sometimes you see one galaxy in front of another galaxy, and this would be along the plane of the Milky Way. That's why we see so many stars in this field of view. So we're looking away from the center of the Milky Way out along the edge, and so we can definitely see the spiral structure of this galaxy. But all the stars in the Milky Way are trying to get in the way of our view. There's another pair that seems to be one in front of the other. And here's what we call a compact group. And so all four of these little galaxies are in a group, gravitationally interacting with each other. So that gives us some information about the nature of normal spirals. And then parallel to them are the barred spirals, which really are interesting because they have this enormous bar-like structure, where the bar appears to rotate as a solid body. Now remember, galaxy bars are not solid structures like a rod or something. No, they're composed of stars and gas and dust, but they rotate as one. So the stars so that means the ones that are farther out are rotating faster in their orbit so that they maintain the bar than the ones closer in. Just in the same way, if you look at a marching band, so yeah, the best example is a marching band. The marching band has to keep its lines together in order to stay as a line as they turn a corner or do their thing on the football field. So the guy that's in the interior of the turn, he takes little tiny baby steps, but the people on the outside of the turn, they have to take huge steps, so they have to go faster or practically run in order to keep the line the same. So in terms of marching band styles, you could think of the bar of a barred spiral as a big marching band of stars. All right, so here's the barred spiral, NGC 1300. So they have very similar characteristics to spiral galaxies, except for the huge bar in the structure. There's another one, the NGC 1365. We can see the various types, SA, SB, and SC. This is an SBA, so it's a large bulge and tight arms. And this is an SBB, meaning intermediate bulge but looser arms. And then we can go to SBC, which are really tiny bulge, very, very well-defined arms, and the bulge is there in the center. Now this also highlights the incredible star formation that is occurring in M83, Messier Object 83. And that's where all the pink glow is, and that's where stars are being born even now. And it's wonderful to take a zoom in to see the effect of that. So those are incredibly turbulent regions, but if you were nearby, you'd have something, if you were in that galaxy close to that, you'd have such a beautiful view in your night sky. All right, here's another view of a barred spiral. More barred spirals. You can see the pink glows of star formation. So these have lots of gas, lots of dust, star formation is going on, young stars and old stars. Okay. Another barred spiral showing star formation in young stars. There's one I use for a lab that I've used frequently. It's a very pretty barred spiral. Here's another beautiful barred spiral that kind of has a ring around the bar, which is interesting. And another barred, and another wonderful barred spiral. There we go. Let's keep going through. And now we get to the second to last of our classifications, the irregular types. And basically, they look like train wrecks. An irregular is not an elliptical, it's not a spiral, has no spiral structure, but they tend to have a lot of star formation going on in them, the irregulars. They look like messes, and these are the two large and small Magellanic Clouds. Now, they're together in the sky, and this is a ground-based photographic view, but then when we take these amazing views of the Large Magellanic Cloud, we see that there's lots of gas and dust, that there's star formation going on, and there's a lot of activity. So there's a huge amount of interaction going on inside of this thing. It's a turbulent place where stars are being born everywhere. The Large Magellanic Cloud is about 200,000 light years away. And so we see everything we see in there, the light has been traveling for about 200,000 years to get to us. Same with the Small Magellanic Cloud. This was taken by Stefan Guissard. And I just got to mention that. I'll find the link for his work and put it on the YouTube channel. But again, this is Stefan Guissard's image, and we see the Small Magellanic Cloud is here, but just to the left of it is a globular cluster that's part of the Milky Way, and below it is another globular cluster, part of the Milky Way. So the globular clusters are, comparatively speaking, on the order of tens of thousands of light years away, but the LMC and SMC Small Magellanic Cloud are about 200,000 light years away. So that means for it to be that big, it must be really huge compared to something that's 10 times closer. So if the Small Magellanic Cloud were at the same distance as the larger globular cluster, it would be 10 times bigger in the sky. So those are big, 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 big things. And that's also a place where star formation is going on. An interesting irregular, which is the active galaxy M82, and I showed you M81 and its neighbor M82. It has some strange structure. You could think that maybe it was once a spiral galaxy, but it has this glowing, it has a dark dust cloud going across it. And then if you take a deep image, and this is a deep Hubble Space Telescope image, that pink glow is ionized hydrogen gas, and the outflow is going at tens of thousands of miles per hour, miles per second actually. It's going extremely fast. These winds have been driven, and it's being driven out to tens of thousands of light years, up to over 10,000 light years long, some of these filaments. And M82 is the brightest galaxy in infrared in the entire sky. And what has happened is that there's an enormous amount of star formation happening inside of this galaxy, and the combined winds of all those super bright O and B type stars creates enormous winds, and those enormous winds drive the gas, and so the gas is being driven out of the galaxy by the formation of the stars. And this is an interesting combination of X-ray, of optical and infrared imagery of the same galaxy, and it just looks kind of like a crazy, crazy, crazy thing. So, right, the center, and this is a more standard sort of appearance, NOAO ground-based image. And then using the Wide Field Planetary Camera 2 from the Hubble Space Telescope, we get the interior of a dusty, dusty area where lots of star formation is happening at M82. And there it is once again in the sky. A few years back, M82 had a prominent supernova that went off that we'll talk about in the future. It's a very, very nearby one, but it was a distinct kind of supernova that's called a Type 1a supernova, and it was very important to help us even more land down the nature of the distance to M82. But you can see in this full color image that the hydrogen gas clouds are there. And yes, M81 on the left and M82 on the right are distinctly interacting. M81 on the left is much more massive than M82, and the interaction has caused M82 to go into a massive amount of star formation as M81 buzzes by. They interacted probably about 10 million years ago or so, and they're at roughly the same distance from us, at about 12 million light years away. So their relative distance between each other is actually quite small. So that's interesting. The interaction that they had, very deep images, show that they're still interacting, and that there's a line of hydrogen gas binding between them that can be seen in the radio wavelengths. And here's another disrupted sort of irregular. Gosh, they look all crazy. Oh, here's another irregular. They just look like train wrecks, like something's really went wrong. Like mistakes were made. And here's a dwarf irregular. And here's another flavor of irregulars that kind of looks like a barred spiral galaxy, but in the center we see active star formation in a ring-like structure. And here's another strange-looking irregular called Hoag's object, which is a Hubble image, and so star formation in a ring. There's another one, the center of NGC 1512, which is a ring-like structure. This galaxy has a bar, and then that bar has a ring, and so it's kind of a double-ringed galaxy, so we'll call this an irregular. another irregular ring structure. And then you get the really strange ones, which are the dwarf irregulars, which are just complete little tiny train wrecks. And they're almost impossible to image because they're compact, dim, small, and difficult to observe. As you can see from these things, they're practically not even there. And the Sagittarius Dwarf Irregular Galaxy orbits our Milky Way, and it's so gossamer that it basically you can see through the galaxy to the other side. So what exactly holds this galaxy together, and what exactly is the lowest boundary for a galaxy? This is an incredibly important topic for, say, the study of dark matter. How does dark matter cluster? And so there must be an enormous amount of dark matter there to keep the Sagittarius dwarf around. And here's a couple of other dwarf irregulars, and we can see active star formation occurring in them. And there are also sites where they're basically train wrecks of interaction. And here's another dwarf irregular galaxy. These are very tiny objects. They tend to have only a million, on the order of millions to tens of millions of stars on their sizes. And they're typically distorted in shape like these are, and they typically have a lot of hot young blue stars in them. All right, so here's some statistics on the nature of the ranges of galaxies. So we look at spirals in blue, and they tend to be on the order of 1 billion or so solar masses up to 1 trillion or so, just over 1 trillion solar masses, or 100, or just under 1 trillion solar masses. The largest, but ellipticals have an enormous range, down to about 100,000 stars, 100,000 masses of the sun. That's what the M sub sun means mass. That little target is a symbol meaning the sun, and M means mass. So we're doing this all with respect to the mass of the sun, and that means that ellipticals span from 100,000 times the mass of the sun up to 10 trillion times the mass of the sun for the giant ellipticals. And irregulars are kind of an in-between group that go from about 1 million times the mass of the sun to some of them can be as large as other spiral galaxies and larger than many spirals. So irregulars kind of span the gamut between them. Now, if we think about the luminosity of them, the luminosity is in different range altogether. Spirals go from about just over 10 million times the luminosity of the sun up to just under 100 million times the luminosity of the sun. Whereas ellipticals range from 1 million times, which is much dimmer because they can be smaller ones, all the way up to 1 trillion times the luminosity of the sun. And irregulars are down there in the tiny ones, so irregulars tend to be much smaller. So that's because ellipticals range in size and mass. And now we think about the diameters of these things, and this is where it gets really dramatic, is that spiral galaxies are on the order of 5 kiloparsecs, or about 15,000 light years, up to about 150,000 light years across, with the Milky Way being about 100,000 light years across. So the Milky Way is on the larger end of the spiral galaxy size. Irregulars are all tiny little things that range from that are almost like 10 times smaller than the Milky Way, up to down to 1% of the size of the Milky Way. But ellipticals can range from being really tiny things to catastrophically large things that can be up to 10 times the size of the Milky Way. And the largest galaxies known are all giant elliptical galaxies, which make the spiral galaxy Milky Way look like a tiny, tiny, tiny little brother. So the structure and nature of galaxies are that spirals have a disk, they have a spheroidal component, they have rapid rotation, and the spheroid is puffed up because of the random motions down inside the bulge. Elliptical galaxies, though, are only spheroid. They're only old stars. There's no gas or dust, and spirals do have lots of gas and dust, which we see with the rotation. And all of the rotation of ellipticals is just mostly random, and there might be some slow overall rotation, but the random rotation of the stars dominates the appearance of the Doppler side. So basically, if you look at one side of an elliptical compared to the other, you're just not going to see that there's one side is approaching you and one side's going away. Spirals, on the other, however, if you can get an edge on, one side's coming towards you, one side's going away. And irregulars, they're just a mix. They're chaotic in structure. They have tons of blue stars and some rotation maybe, but there are lots of chaotic motion, so they're stirred. All right, and spirals, in terms of how many stars and gas there are, spirals are about 10 to 20% gas, a huge amount of hydrogen gas. Lots of star formation is going on in the disks, and there's a mix of the, I remember Walter Baada's combination of population 1 and population 2. There's a mix of population 1 and 2 stars, meaning some old stars, some really ancient stars, and some really new stars. Ellipticals, there ain't no gas nor no dust. And star formation ended a very long time ago, and there's only population 1 stars. Meaning, even if you take a spectrum of it, you find that even their chemical composition is ancient. Irregular galaxies can be almost all gas, and so there's huge amounts of star formation going on because tons of gas means tons of things that you can make stars out of. So they're pretty much, you see, only population 1 young stars, meaning O and B and A type stars, or F and Gs, sure, but dominated by the bright ones. And dwarf ellipticals, they're very, very, very metal poor. And so they may very well be, because of their low mass and small size, are just finally getting to the point where star formation can begin since their formation over 12 billion years ago. So that's really interesting. Dwarf galaxies are most common in the universe by number, but not by mass. They're all, and all of these are either small ellipticals or tiny irregulars. There's no spiral dwarfs, meaning little tiny dwarf galaxies. So remember all those images I showed you with there's little tiny spirals? They're far away, that's what we mean. And the dwarf galaxies might be just smaller versions of the larger ones, or they're a completely different population of objects, and they seem to be the same, but yet the dwarf galaxies might just have the similar appearance to them, just scaled down, but their exact nature is an area of active study. The most important element, though, and the takeaway of this is, though, that we're going to take in the future, is that galaxies are the basic units of luminous matter in the universe. They are, by basic, what we mean is that they're the things that when we say we're looking at a supercluster of galaxies or a galaxy cluster, now we're not looking at individual stars, we're looking at groups of galaxy clusters, which then also group into groups of groups called superclusters, or just a really big group of galaxies. And so where you find star formation in the universe is in galaxies. Star formation doesn't occur outside of galaxies. Star formation only occurs in galaxies. So therefore, galaxies are the place where heavy elements other than hydrogen and helium are formed in the entire universe. And so we've got to find that the different kinds of galaxies mean that there's something different by how they formed and how they evolved and where they live. And that's what we're going to talk about when we talk about the structure of the universe. So here's some wonderful little appearance questions, some review questions for you to go over. Have some good time looking at those things, and we'll see you next time.